Hello and welcome back to this Groundwater online conference. My name is Helen Gibson. I'll be speaking for the next 40 minutes. My segment today includes introduction to creating implicit 3D geology models, plus tricks for modeling thin units and for exporting to codes such as MODFLOW and FEFLOW. Validation of approaches is something important to begin with. Next, we will move into introduction of creating implicit 3D geology models, and that will include demonstrations of building a rapid 3D geology model in GeoModeller software, exporting geological information to MODFLOW, mesh exports, and some other tricks to do with applying clips to your model. Further materials will be shown before the close of the session. Validation of the approach is an important step. It means that you've decided that numerical modeling will be part of your workflow to achieve a quantitative approach to groundwater resource assessment and ongoing management. The next important decision then is about choosing to model fully in 3D, choosing to attribute your mesh with physical properties which can directly relate to 3D geology volume domains present, and the location of faults in your field area. Choosing to build a realistic 3D geology model constrained by geological observations is also a very important choice. We recommend that only incorporation of 3D geology can lead to a realistic and reliable numerical model. The number of choices available for codes which can build implicit 3D geology model and then export geological information to a waiting mesh or provide a direct mesh export are quite limited. However, today in this lecture we are going to choose one of the codes, being GeoModeller, and provide some theory and practical steps for achieving the workflow you may require with an intuitive software interface. There are three stages of rigorous 3D groundwater resources assessment. Geological modeling, in terms of consolidation and reconciliation of legacy data, including all the hydrostratigraphic units, honouring primary geological observations, and finally generating the verifiable 3D geological and structural model. Conceptual modeling is at the heart of stage 2, and that means you're ready to review the characterization of the aquifers and view in 3D the locations of faults, fault compartments, and their connectivities. Understanding flow systems, including their pathways, flow directions, springs, is all part of the system to be understood, and you can do this visually. The next thing then, moving from the qualitative to the quantitative, is about calculating in the volumes of different hydrostratigraphic units and then moving on to a reserve estimate. Hydrogeological modeling is then about the numerical modeling on a mesh, moving into the realm of other properties related to geology, but moving into the mathematics. One such case study available to us to illustrate 3D rigorous groundwater assessment is now published in the Journal of Hydrogeology. With permission from authors, we recently presented this study at the 4th European Meeting on 3D Geological Modeling, held in Orléans, France. Here again today we show some of these slides and present the steps taken to rigorously assess groundwater resources in the Kasserine aquifer system, which is located in central West Tunisia and eastern Algeria. The Kasserine aquifer system comprises of 5 hydrogeological units, 3 main aquifers and 2 interlayered aquitards as shown here. In the upgradient aquifer system located west, mid-Miocene sandstones 10 to 300 meters thick are unconfined and shown by the bright yellow. The downgradient system in the central east comprises Miopliocene marls 400 meters thick at the greatest, and they are confining the middle Miocene aquifer in this region. This is shown in the pale yellow outcropping unit. Data available to build the CAS model are summarized in these tables, comprising digital elevation map, geological maps of varying vintages, 3 cross-sections in a published study, and 173 bores. Steps to build the CAS model in GeoModeller software are shown in this slide. Firstly, unification of stratigraphic classification region-wide is importantly performed. This means that some units will be merged, but other more important hydrostratigraphic units remain separated in the stratigraphic pile. After geolocating the map images, shown lower right, into the 3D workspace, the job then is to digitize geological boundaries as contact points, and also to add the dip direction data in their 3D locations. Next, in GeoModeller, it's possible to load geological logs relating to the bores drilled. In this study, only 47 of the most representative and deepest wells were chosen out of 173 available. Next steps to build the CAS model include geolocation of section images. This then enables digitization of contacts and dips in their 3D locations, and as this is done, more and more data can be added to the model and recomputed and re-rendered at any time. This enables constantly checking the model in 2D against a 2D section, such as shown below. At any time, the 3D geological model is available to us in different rendered states. Here is a summary view showing the completed regional scale model, which honours primary data, includes the digital elevation map, and is shown here for its full extent at 100 km by 75 km by 2 km in the Z direction. This brings us to an important rhetorical question: why map geology in 3D? The best answer, perhaps, is to say that we have enabled the possibility to validate continuity of geology and fault structures everywhere in 3D space, whilst also allowing for the topography to be an important constraint of the model, because this influences the outcrop pattern. Next steps for the case study include what we call review of the conceptual model, characterization of pathways, connectivities, location of faults, springs and bores all make up part of this visual exploration. As well, we make use of GeoModeller capability by a process of discretization of the implicit model into a block model. When units are described in this way, we have access to the metrics of the model, including volumetrics. It's an easy step then to calculate the reserved volumes of aquifers and also apply porosities and storage coefficient estimates against these to compute final resources in groundwater. And in one man's workflow, this could be conceived to be the end of the conceptual modeling process. And the final stage is about hydrogeological modeling. In this sense, we are illustrating a coupling of GeoModeller software with FEFLOW software to accommodate this. This particular technology shown is a layered finite element mesh in which a fill centroids menu in GeoModeller was used to indicate the geology at different spatial locations, and therefore to enable population of various attributes into the mesh. What then followed was steady state and transient flow modeling in FEFLOW. The choice of GeoModeller in this case was about the successful ability to combine contact observations on formation boundaries and couple these with dip and dip direction data. GeoModeller also employs a rule-based modelling approach whereby relationships within the stratigraphic pile models constraints, as are the relationships between faults. Also, in GeoModeller, you can include only surface data from your map and very limited or no drilling data at all by which to build a 3D geological model. Additionally, multi-geophysics integration in the 2D and 3D workspaces is a very handy way in sparse data environments to add more geological knowledge, particularly to the deep parts of your model. Easily editing and recomputing the model is absolutely important, and it goes to speak towards the maintenance and future groundwater resource management systems. But perhaps one of the best features is the interoperability of GeoModeller to flow codes, where GeoModeller is enabling the export of meshes or points in terms of informing geology to the future flow mesh. So at this point, it's important to review the fundamental underlying equations in GeoModeller which compute implicit 3D geology from observed geological observations. This is performed by a co-kriging mechanism where two related variables can be included. These are, and looking at a map view here, where green sandstone meets blue sandstone, we've got points of observation on the boundaries. The points of observation for the boundary can be combined with the dip or the gradient of that field. And these, as we know, structural geologists collect them in the field all the time. It's a dip and dip direction, otherwise known as an azimuth, and a dip from horizontal. So the way it's done for these two related variables is the geological contacts are treated as if they're ISO values of an interpolated 3D scalar field, and then the dip direction data is treated as a gradient of that field. In this way, the model doesn't simply join the dots between the green points to make a straight line, but you can see it's taking into account the curvature of the field related to the dip direction data, and this does not have to lie on the contact of two geological units, as is typically the case. And now, considering multiple potential fields altogether, we build up a stratigraphic pile, you see, as part of our user interface, and this allows us to include semi-concordant geological units and group them into what we call series. A potential field method of interpolation happens per series, and this means you can build a pile with onlap or erode relationships which are going to be processed after the interpolation of each separate potential field. The view on our right is a cross-section whereby we're starting to add observations for the boundary locations, let's say known locations for the bottom of the green formation F3, together with a piece of dip data for that F3 series. When we've satisfied the minimum requirement of contact data and dip per formation, we're able to compute that formation. Each series in the pile is interpolated separately, and then the relationships between are processed. Note in this example, the stratigraphic pile makes a change from the left to the right. The base of the blue meeting the yellow is onlapping on the left example and eroding on the right example. These create two very different models. So what we say is this is rule-based modeling because elements of relationship within the stratigraphic pile are also constraints of the model. So what about faults? GeoModeller can also treat faults by a rule-based modeling approach. Why? It's because rules can be set up as linking faults to affect certain geological series and not others, and faults which stop on other faults. In terms of the theory and presentation of a case study, this completes the PowerPoint section, and now I'd like to move into demonstrations which can actively show workflows about rigorous groundwater resources assessments. Welcome to GeoModeller 4. In this demonstration, we're going to review an existing project which has been set up to show a steep digital terrain and a simple pile of units A, B and C. We can see that this is 5 kilometers by 5 kilometers in the X and Y directions and 4 kilometers in the Z direction. The projection system is local setup, but there can be any number of world coordinate systems available for your own setup. Having a look now at the wireframe, we can see in the 3D viewer on the right hand side that the digital terrain model is a grid which is now loaded and showing as the top of our wireframe boundary condition. Additionally, moving to our north-south section as drawn, currently we have some data points here already which relate to the geology objects in our pile. The description here are points for the bottom of Unit B, being the yellow unit. Reviewing these data on the section, you can see that how that was selected was to literally draw points in section north-south, and if you're watching the numbers at the bottom left hand of your screen, you can see that these are at minus 519 meters below sea level now. There are 3 points describing the boundary of Unit B, and there are 3 dip location directions shown also. 3D representation of those data are available to us as well on this section. Displaying the section now, you can see the data here in the 3D viewer. First thing I'm going to do is now compute the model for the 1 series B and take into account the sections which have data, which is only 1, and proceed to compute. When that's done, the potential field method applies co-kriging to the dip data as well as the contacts, and then we're able to see our first modeled variety of geology. Hiding the section now, we can take the model geology across to the 3D viewer. Notice how if we had not included the 3 pieces of dip direction data in our compute, then GeoModeller would simply have just joined the dots between the contacts here. That's not the case because we're including the co-kriging equations in implicit modeling of this boundary. Let's just see now how the GeoModeller interpolators are working. If I repeat the render of the 2D section, I can alternatively show the fill for the basement unit C, but show trend lines instead for unit above. For clarity, I'm going to increase the number of trend lines available to the view and apply the render. What's shown now is a 2D representation of the field lines akin to bedding. GeoModeller understands these as tensors, and we are able to bring out those data in terms of flow line vectors to inform a flow model such as FEFLOW, who has the capacity to take those in as attributes of a mesh. Another thing to demonstrate is, of course, the GeoModeller model is clipped by the topography surface, and let's have a look at that now for a minute. Looking on the surface topography section, GeoModeller keeps a copy of all the grids it needs in the model project, one of these being the DTM. Visualizing that now on the 2D surface, you can see this is a grid brought in at reasonable resolution, and now we are able to have a look at the histogram of that because of course it's natively handled, it's a .ers file, and there's a histogram available for the frequency of different elevations between 623 and 1569 meters above sea level in this case. In the next part of the demonstration, I would like to show how you can add a thin body to this geological setting. Let's return to the data we have on the north-south section. Supposing we had an angular unconformity between unit A and B. Taking the Create tool, we can simply draw what we think might be the representation of this bedding of unit A. Creating those points is as simple as digitizing them to section and asking for these to be now assigned to the bottom of unit A and creating them. Next we need some dip direction data. Again, take the pencil tool, and in the plane of this section we can automatically create three-dimensional dip direction data. Making it assigned to A again, we can create that now. Let's visualize our data for unit A. And zoom in now. Even though the data have a place in the 2D section, they are also described in 3 dimensions. We simply recompute the model, including series A as well as B, and then render the model again. In this case, unit A gives way to unit B, but we can change the relationship in the pile to make that different. Unit A is onlapping, but we can change that, recompute the model, and re-render the model. And this is the model shown with unit A with erosional relationship rather than onlap. Here demonstrates the simple way in which we can fundamentally create thin units which pinch out against one another. It's time now to look at our solid 3D geology model. Let's firstly hide the DEM and then build in 3 dimensions what is the effect of our current model. This is at low render. You can see it was quite quick to build. If I want a higher render, that's also possible. Let's take it across and repeat. There we have our first solid geology model with a thin unit pinching out. And let's now just view that also as a map on the surface topography section. The next part of the demonstration is going to be about exporting geological information in ASCII format ready for MODFLOW. One of the simplest ways to do this will be to discretize our implicit model now, then take a surface on which we would like to export points. We start by taking the 3D geology model and create 3D grids with physical properties. We're going to choose a fixed cell size. 400 meters is fine. Okay. This is created very quickly below. We'll just hide now the implicit geology model. And the remaining step now we need to do is fill this new 3D mesh. That means add the current model field from the implicit 3D geology. Let's have a look at it now. Visualizing it in 3 dimensions. And you'll see it is a block model. It's a discretization of our model. In this format, the stratigraphic pile is also able to help us. Have a look at the numbers now. Number 1 is assigned to the orange unit, and of course we can do some mathematics with numbers. The final step is to ask for the center top of each of these cells to be put out as a point. To do that, we right-click, Export Surface Shells. We request out of the possibilities voxel tops in CSV. We write out the file. We state the value is unit 1. Next we can import that back just to view it as a 3D set of observations. This will take the wizard method importing the X, the Y, and the Z value as the field. When we've done this, we're able to view the values in the 3D field. The CSV can now be taken off usefully to MODFLOW. For the next part of our demonstrations, I'm going to move to a more complicated model. This is geolocated in southeastern Australia. It's known as the Mansfield Syncline model, and it is part of our training material. Project Properties reveals some further information about this model, which is that it's 17 kilometers by 17 kilometers by 3 kilometers in the Z direction. Additionally, you can see there's drilling constraining this model, as well as a considerable amount of surface data. And just to show you a little bit of detail of this Mansfield model with some variations, we have included a finite fault as well as an infinite fault, one here that charges right across the model and one here which is limited. We've also added to it a dike. One final note before we launch the menu is to remind you that this is not the mesh you're going to be outputting. This is created by the regular visualize tool in GeoModeller, which is a marching cube approach. Now we're ready to commence the export of the mesh. In the main menu, select Export 3D Model Model. This launches a dialog box which enables you to set up the parameters of the mesh. Let's browse and save. Next, we choose the 3D export type, which is FEFLOW, and press OK to launch the mesher. And now let's take a look at the products that were generated. So we have this FEM file, and we have a .data file being the triangulations. The next thing to do is to launch FEFLOW, and then we're going to just drop and drag the new FEM file. This action launches a 3D viewer and a 2D slice viewer. I'm just closing that for the moment. And here we have the first recognition of a layered finite element mesh by the user data. And next thing to do with the 3D viewer activated is to see the user data and double click on rock type. This loads the geology into the elements of the mesh. There is some nice work in the triangulations. Another thing to notice is some adaptation to the layered mesh around angular features of the geology. Additionally, this mesh will be watertight and manifold. Returning now to the GeoModeller interface, we're going to have a look now at one of the last export modes. It's the fully unstructured finite element meshes, now available in the latest build of GeoModeller 4, and utilizing Seagull libraries for construction of tetrahedra as well as triangulations. Proceeding to the tetrahedron meshing main menu, the green triangle, this launches a wizard. The first question is whether or not we're going to select to preserve triple lines. Triple lines are where 3 geological compartments or 2 compartments and air come together, and it's about asking to preserve the exact location of the implicit surface as solved, and therefore delivering these will include a very aesthetically neat mesh. However, it's not compulsory to compute including the triple lines. Proceeding without, the next menu talks about the meshing criteria. This is delivered on a per unit control mechanism, whereby you can set individually the precision of each geological formation. Refinement settings are an advanced topic but we don't need to set them. Next, we do need to set the type. FEFLOW and VTU and many other options are available to us. If you want to add a second one, it's available at the same time. Let's proceed now to request the FEFLOW and VTU output. You get to review the batch script which is running underneath and proceed to finish. The console represents the progress of the task of performing the meshing. When it's complete, we can load the mesh. Let's just review in the Windows folder where the products have been written to. Inside the GeoModeller folder, there's an export mesh folder, and here are the products that we requested. .gmod file is the special that we directly export to FEFLOW, including the two .dat files. VTU and VTP represent unstructured, generic mesh formats. We can load directly into GeoModeller to assess the product by import, triangulations, and browsing to the export mesh folder. We can load the VTU. These are all the nodes of the triangulations. And these represent the faces. A separate file was generated for the faults we can import now. VTP, and show that independently. Alternatively now, we can launch FEFLOW. The steps to load the Gmod file are as follows. File, New, Fully Unstructured 3D Mesh, Next. From a Super Mesh import from Maps, Next. Add the correct file. Searching first for the Gmod file. Finish. Just in the 3D viewer now, we can pan and rotate the product, which is our GeoModeller derived .gmod file as a SuperMesh import. I'm not going to proceed to bring in the area constraints via the .dat files, but this is something very familiar to FEFLOW users. Just in the remaining time available, I'd like to finish by showing you a trick for applying a watershed outline to clip your model. This alleviates the situation where the 3D geology shown today is restricted to an orthogonal orientation in the north, south, west, east axes. In order to prepare for this setup, we need to go into Geology Formations Manage and make a new unit called Outside Model. Next, we go into the Start Stratigraphic Editor, and we can straight away create a new series as an erosional relationship. Now bringing the Outside Model unit up to the top and close, and just check the stratigraphic pile construction now. See that Outside Model unit is now the youngest, and it has an erosional relationship cutting every other stratigraphically older unit in the model. Closing that now. We also need to show the digital terrain model because this will help to guide us around the watershed zone. I'm just approximating this to the ridges at the limbs of the syncline. You see it's following me now in the 3D viewer, and that's enough points. If we now commit those to the outside model from the drop-down list, at the same time we're going to add some associated orientation data. This is a quick way to build into your chain of contacts. You can make some dip direction data automatically quite easily straight away. And we'll just view that now. And that's the sum of what we created. On a vertical dipping scenario, we selected a polygon onto the surface topography section and saved those points. Next, we're going to recompute the model with everything included in terms of series, the new outside model series also. Select all. Straight away it's done, and we can build again the model. When the model is complete, you'll see that you have the choice now to hide the outside model. This leaves precisely a limited model clipped to the topography as shown by the DTM. So it literally becomes a neat way in which to reject some volumes and not have them included in your meshes as you take them out into various numerical flow codes. So herein ends the demonstrations of today. I'll just return to some closing remarks. And so the further information that I will direct you to is the Intrepid Geophysics YouTube channel, whereby we have a number of similar video but longer content. Firstly, of interest may be a little bit more detail on the MODFLOW, interoperability, and finally a little bit more information about the FEFLOW interoperability. I hope you've enjoyed today's lecture. Thank you very much for your interest. Please keep in touch.